A new sections, okay, walking out of the local analysis. We have gone through the variable representations. The first thing we do, exception and things. We went through the local analysis, give you a general treatment of how do we deal with differential and integration, okay. So now the next tool that in your toolbox will be something in the linear algebra domain, okay, especially in the sparse matrix, okay. So not only that I'm going to introduce this, again, a topic that you may know very well. There's along the way, this is a good example, okay, of how you should write different level of testing. Okay, so along the way, so in addition to the usual linear algebra that you will see, from time to time, the idea that any operation, okay, can be verified, and how do you write a modular testing for the operation you're going to do is going to be deeply embedded in this topic. If you take a step back, okay, any problem in the world after linearization is linear algebra. So it shouldn't be easy, right? If it's easy, the world will be easy, right? So there's a lot of content in here. Some of them that you probably definitely have seen before, okay, because of generality. So first is the, when we treat this, there's a large number of degree of freedom or independent variables, okay. So this we briefly mentioned in the beginning of the class, okay. Let me just review very quickly about that, this is the real world, okay. A Dow Jones index has about 10 to the 7 variables you need to consider in order to do anything. And it can be a nonlinear question, okay, if you consider the interdependencies or the future forecast feedback to the present price index, okay. So it's can be a nonlinear problem, okay. And I use the weather simulation as an example, right? You can easily see that in this very, very coarse grid, on the not very large area, very coarse grid, you have 10 to the 11 variables. Okay, so when these 10 to the 11 variables, they depend on each other, okay, then this become a very, very large problem. Okay, very, very large problem. And 10-meter grid, is not good enough. Okay, you walk around, you have a cold breeze on your face, that is not representable by 10-meter grid, right? So, but that's already as crazy as this number, okay? So that's something, but it's totally not enough. So it's when you have even larger and faster computer, there are many, many other things you can do, okay? So this even on such a coarse problem that I cannot deal with it directly, okay? I need a sparse system to deal with it, okay? I'll tell you about the sparse system immediately. So for ECE things, right, I'll use this one as a more examples, okay, that an ALU, okay, typically today 64 bits ALU, you have about 10 to the 7 internal nodes, okay, about 3 to 5 million transistors, okay, so that represent your ALU, okay. But for sure, this is not your whole microprocessor. Your whole microprocessor contains about 5 billion transistors and about 10 billion nodes, okay? So 10 to the 10th, okay? A little bit more than this, okay? But even you just want to, but nobody do circuit simulation directly on the entire microprocessor, but ALU many times for the optimization of timing, timing budget, power consumptions, and all these things, you still need to do circuits. When you do circuits, then we're dealing with these kind of internal nodes, okay? And it's all the transistor or the switches is nonlinear, okay? You're solving a nonlinear problem with this kind of number of variables, okay? So this is not uncommon, okay? So using this example, okay, just 10 to the 7th, okay? So if you try to map a data bus, which is the output, to the internal nodes dependencies, okay, then you have to deal a matrix of this size, okay? Or if you try to do transient simulation, okay, that you want to map your present nodes at t equal to t0. You want to predict the behavior of t equal to t0 plus delta t. You are going to write a matrix that's of these things, right? A matrix that can map 10 to the 7 to another factor that's 10 to the 7. Okay, in general, a matrix representation, that's 10, 7, 7, right? So in arbitrary, right? So you can go to whatever state and things. If you want to do a transient simulation of this kind of number of variables, then this is the matrix that you have to deal with. And if you want to try, please have your computer declare a double A of that dimension, okay? And Python should kick you out directly, and your C should not compile. Okay, feel free to try, okay? 2 lines, that's this not, you declare this. This is not a legal statement because this is the storage that's required. Right, so kick you out, okay? It's just something you can imagine that future computer can handle this or things, but this is one simple ALU, about 1/20th of the circuit in your microprocessor. Okay, so this is not possible, okay? So it's definitely we need something better. Some way you just cannot, even for today's smaller scale problem, you cannot treat problem at its face value. You treat the face value, you cannot deal with it, okay? Does Python kick you out? Does Python this? What?
I'm not using Python.
Okay. Okay. Python is interpretive, should kick you out directly, okay? Anyway. So the idea of a sparse matrix is this, okay? So most of these mappings are sparse. The 10 to the 7 variables and the other 10 to the 7 variable in the next time step, they are not all related together. Actually, the relation usually is very small, okay? The whole matrix is large, it's a big, that one can trickling down for another, okay? But if you only look at local, okay, the interdependency is not give you a full matrix at all, okay? Using this as an example, okay, ALU circuit. Usually, a circuit node is at most connected to 10 other nodes, okay? Right? So you have any of the circuit, right? You have transistor and things. This node, even if fan out, okay, for other things, right? It doesn't connect to all the other nodes. It only connected to maybe on the average 10 nodes. There will be nodes that may have 10,000 connections. That's the data bus. But not a lot of nodes like that. Okay? There will be nodes that have lots of connections as a data bus. Okay? But most of your local nodes have very few connections. Okay? So on the average, all of a sudden, if you on average they have 10, then you only have to store 10n instead of n squared. N squared is not doable. Okay? Only 10n is doable. Okay? I'll show you immediately. Okay? For a finite element problem, okay, 3D formulations, okay, if you write down a partial differential equations, then, okay, if your formulation is only your nearest neighbor. In 3D, in a grid, right? In 2D, you have 4 nearest neighbor, right? In 3D, you have 6. That's about it. 6 plus 1, you always connect to yourself, okay? So this is 5 connections, and on the 3D is 7 connections, okay? On the boundary, for sure, there will be nodes that connect to a lot of a boundary, an electrode, something, or a fixed temperature plane, okay? On the boundary, you may have things that are much more connected. But on the average, this is the number that you have to deal with. Okay, so when you're handling this, whether it's a video games where you have large pixel, right? Not every pixel change regard with the pixel far away, right? Your video make progress gradually, right? So video games, star market analysis, not every index couple with each other, right? They have local coupling. Or engineering simulations, okay? Sparse matrix. You have to deal with a relation that's large, but most of the relations are sparse. Okay, this is 101 idea we have to treat, okay? So, since this is such a historical and big problem, so So there are all these resources, okay? These three are the one most popular. Okay, I'll tell you a little bit story about this. Okay, four actually, MATLAB. Okay, BLAS. Okay, you should. This is developed in the early 1960s. Okay, and still used today. Okay, BLAS is it's highly optimized. It's written in Fortran in the beginning. Okay, it's used to handle all the matrix and sparse matrix operation and solutions in these very legendary code, and they are still code. You use BLAS, okay? It's just now we have C routines you can call, okay? It's highly optimized when there's no branch necessary, okay? It's no branching, okay? BLAS is so highly parallelizable, okay, that it runs very fast on vector and parallel machines, okay? Many of the techniques that we talk about for exceptions, okay, it is almost developed for BLAS. Okay, so why exception need to be handled in that way? One word, okay, you cannot always check. You have to let exceptions to propagate by itself. If you check during debugging, that's great practice and everything you should understand. But during actual computation, check, break, parallelization. Period. If I can only make computations based on some values, there's no way to parallelize. Okay? Parallelizable or parallel programming means you want to reduce the data dependency of each computation. I'm done. Okay, so you can take a special course to go through all the MPI and all these things for parallel programming, but it's one word, right? Anything that needs to be parallelizable, you cannot check the exception. If you check a branch, commands cannot be parallelizable. Or if you really have to parallelizable, you make a speculation. When the speculation is wrong, you have to retract. Right? So that's constantly done. Okay? So the best way to do any parallelizable things is that you cannot check. So if the exception happens, you have to let exception propagate. Okay? So this is the spirit of BLAS, okay? In the way that you rely on the exception handling capabilities to give you the fastest code possible. Okay? And for a large problem, you can imagine in the old days that there are many problems that are significantly large and you need real-time response. Airplane control, right? If you don't have a fast computation, you're absolutely dead, right? So in many ways, so this is highly optimized for that. Okay, so you can, I give you all the link. You can take a look at your C library. You'll see many things. They even consider how the data structures of your vector and matrices. I'll introduce a little bit, so that the cache operation is most efficient, right? When you use the data, okay, a fast computation means that I want to minimize loading in new variables. Because loading in variables from main memory is 20 times slower than process something in the cache. So if you not only to decrease the data dependencies, you decrease the data dependency along time, make your code a lot faster. Okay? When I grab a value, I use it until I no longer need it, then I grab the next value. Right? So if you do this in random order, then most of the time your CPU is fast, but most of the time you're just loading data to your cache. Okay, so BLAS is optimized for that. So all the way that the data is handled, it consider that I load the data. If there's any further operation required for this variable, it will finish right there and there, instead of before they load another variable or another vector to deal with it. Okay, so this is highly optimized in that sense. Okay, but it's not the key things we do for parallel programming. So it's just that, okay, I'll stop it here, but it exists for this very purpose, okay, to maximize your computational efficiency. There are two other sparse matrix library which are popular supported by US government, okay, so somebody's job is on this, but it's free, okay, so these are the two, okay. I like this one a little better. Last year I used SparseLib, and I eventually write a bug report to NIST saying your software is pretty buggy. I'm really sorry. So, but it's by NIST, so that's I'm a little bit disappointed in a way that NIST have a version 1.7 release that's still that buggy. Okay. Anyway, so this, but it's hopefully they will improve from there. Trinos, okay, it's a Sandia National Lab things. For sure, these are all the weapon simulations and nuclear reactors things being done. I hope that this one I try also, but I didn't try as extensively as SparseLib. Okay, I cannot tell you how reliable it is, but but I look at the code. Okay, so if you want to see a well-constructed C++ programming, good example. Okay. The software programming is done very well. I haven't been able to do the extensive testing to tell you how reliable it is. Okay, so these are the free resources. There are many other sparse matrix, and I will teach you enough to differentiate what is good and what is bad. Okay, there is a fundamental trade-off. Okay, in every sparse matrix handling. Okay, how that detailed trade-off is called the pivot on the run and minimal fill-in. Okay, that even as we have math today, is not a solved problem. Okay, so how do you do something that you will come up with very quickly? How do you do minimal fill-in? A sparse matrix remain as a sparse matrix, but simultaneously maximize your precision, called pivot on the run. Okay, how do you make trade-off between these two? Okay, these are, there's no optimal solution. Okay, so every sparse package have a choice between how they handle fill-in and how they handle pivoting. Okay, fill-in I'm going to teach you very soon. Pivoting of matrix is nothing but the precision exercise you have been doing. Imagine you have a large matrix. After all these large operations of large number subtract each other and get a number with less precision, will that effect be magnified? Okay, that in the matrix I'll show you how that happened, and how do you be able to do your operations knowing that this kind of precision issue is there, that you can do the best job you can. Okay, it's called pivoting. Okay, but this will be entirely introduced. Okay, in very careful steps in tell you how matrix pivoting can be done. Okay, but the trade-off between pivoting and the fill-in is something that every sparse package choose different method to do and to see how great it is. Okay, but there's no optimal solution. Okay, it's not a solved problem. Okay, not a solved problem. There actually still remaining many of the math problems not solving for practical problems. But because they haven't been solved, that also means that it's so difficult to solve that the probability that it will be solved in the near future is not very high. Okay, and matrix operation, that's one of them. Okay, how do you do pivoting with minimal fill-ins? Okay, MATLAB for sure is another choice, but it's not free. Okay, MATLAB, you can see MATLAB. The strongest point of MATLAB is handling matrix and vectors. Okay, sure. Okay, no doubt with that. Okay, but it's just that it's not free, and if you have your own company, you cannot use your software to MATLAB to develop your software. Okay, okay. So sparse matrix representations. Okay, I'm going to teach you the only data structures I'm going to teach you in this class. Okay, and it's necessary. Okay. It's against the OOP principle. Okay, any objective-oriented principles, I should never teach you data structure, right? Because every module is supposed to only API it's presented. You should decide according to API. All the data structure should be hidden, should be private, right? But matrix is one exception. Okay, that the whole point of dealing with sparse matrix is I want to use efficient memory. So data structure is not avoidable. The good news is if your matrix is handled correctly by memory. Anything else doesn't take memory. Seriously, your counter, your algorithm, your whatever other declaration, your defined global variable, they don't take memory, okay? The only thing that really take memory in any of the real things you're doing is matrix and vectors. So if you can deal with matrix and vectors memory efficiently, that's all the memory you have to deal with. Okay, so I am going to dig down into the data structure level, okay, for this particular problem, knowing that in OOP I should never teach that, okay, but this is one exception, okay. But if you handle this, your memory is fine, okay. Your memory handling is fine, okay. So let me make a few assumptions, okay. Most basic operation of a matrix time a vector become matrix, right? So these are just dimension mn mapping a factor of m to factor of n, right? So this is something that we only need sparse representation of A. Okay, vector we don't deal with the sparse allocations because vector, in comparison, if there is a matrix, then the vector is much smaller. So all vectors I'm going to deal with as a full vector. Only matrix I'm doing sparse matrix. Okay, so only A is important. Okay, so I'm also going to assume that most of the practical problem you have a square matrix. Okay. For sure, in general, when you compute some output or something, you are going to use this asymmetric matrix. But no, but most of the difficult problems, I have a row rank and column rank is the same. Okay, I'm mapping the factors to your future steps, okay, to your local analysis and things. So if the mapping is from a factor of n to another factor of n, you have a square matrix. Okay, and I'm going to focus only on this. Okay. So the first step is easy, okay? It's called the coordinate storage, okay? So it's a big deal, right? This is easy, right? So if I have a sparse matrix, meaning I have many zeros, okay? Zero is by default, right? So I only store the non-zero values, okay? For sure, here the matrix is not so sparse. It's 12 elements within 25 locations. But this is for illustration, okay? Many times there are like, you have 10 to the 14 locations, but you only have like 10 to the 8th variables. Okay, it's much smaller. Okay, so but let's in order to show you the sparse storage. Okay, so these are the way called the coordinate storage of a sparse matrix A. Each value have a row and column index. Okay, this is C, not in zero index. Okay, so this is 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. These are just a row and column index. Okay, of I store. So this is good, okay? It's 12 non-zero within 25. And the good thing about this is that this one doesn't need to be sorted, right? If I add an element, if somehow that this 0 flip from 0 to 13, I can append it here, okay? There's no assumptions on the order of your elements. Even though I declare a vector that's in this way, but there's really no assumptions on the order of the elements. That makes the add and delete very straightforward. Okay, so this is just simple.
But it will be slow, right? Because,
yes, totally. You number 101, you handle any vector, you sort it, then it can be many operations can be done much more efficiently. True. Okay, I'll immediately going to tell you what is the sorted the storage. Okay, indeed. Okay, so when you deal with a big data set, you are always facing with this, right? Should I maintain the order? Right, that's a programmer's decision. And many operations, search and everything, assorted data for sure is much easier. Okay, if it's unsorted, then it's okay. So now come the two possible sorted compressed storage. Okay, so this is still easy. Okay, so let's look at the compressed row storage. Okay, so one, I get a pointer of row pointer saying that how many non-zero element is on the first row. Okay, so if I give here, I give row index is start from 0. Okay, from 0. My next row start from 3. Okay, that means there are 3. Okay, 0, 1, 2, 0, 1, 2 3 non-zero elements on the first row. Okay, so I recorded 1, 2, 3, the first 3 elements, their column index. Okay, their row is, these 3 is on the first row by the row pointer. It does assume that the data is sorted, right? The first row, all the data in first row come first. All the data in second row come second. All the data in the third row comes with all these pointers, right? You can use a pointer in C, and you can use just a Fortran index, right? This is also a good example. Is you can see this one as a pointer. Okay, you can see this as an index. Fine, either way. Okay, so these are the compressed row. For sure, equivalently, this compressed column. Okay, so this is the how many. The column pointer is how many non-zero elements is in the first column. Okay, so this is start from 0, and then the next pointer is 3. That means 0, 1, 2 belongs to the first column, compressed column. Okay, so nothing special. Okay, but assume that it's sorted. Okay, assume that is your data is sorted and is stored in this manner. Okay, stored in this manner. So not only because it's sorted, it's slightly smaller in storage, right? Because the row pointer is not a full matrix. This is order n, right? This is only order n. The value and column index in this compressed row storage is the number of non-zero element, while your row pointer is only the rank. Slightly smaller, okay? Probably storage way, it doesn't matter, okay? Yes?
Row pointer, why is it 3 for value 2? Is it because 1 consumes 3 bytes?
Why does he start 1 from 0?
Yeah, why does it 2 has 3? I didn't get that.
Okay, 3, okay. So the first row have 3 non-zero elements, right? Okay. So it tells you, okay, the first row, okay, start from 0, okay, and the next 3, okay, these 3 tell you that 1, 2, 3 belong to first row.
Okay.
So, and these are the respective column index. So so this one, right, 3, these 3 is the one when you want to get the second row, what is the pointer to jump to, right? So you jump 3, right? Jump 3 for this, okay? For sure, in this format, even this 0 doesn't need to be stored, right? Because it always starts from 0, right? So this is necessary, right? So 3 means, right? So when you compute, right, your first 3 entry, your present representation is on the first row. You grab the first value is column index 0, 0, 0. 2 is 0, 1. 3 is 0, 4. Right? And now you have finished, right? You jump to the next row pointer. These 3 tells you now this column, these ones, these 4 and 0 belong to the second row. Okay? And in your mind, I'm going to have you do that the programming immediately. Okay, let me finish introduction for this. This is naturally the increment, right? So when you write your program, your A, where is this, right? This thing is nothing but your row pointer of the row index, right? You keep on increment this, and then you have the column index, right? So this one is added on to itself, right? So it's just like, right? Which element is the start of the second row? Okay, and because I already know its second row, so I can deal with the next, right? I know its column index, I know its second row within this one, right? So I know its exact row and column index to know the non-zero element. And this is convenient in traversing, right? So when you want to go through all the elements in the matrix, right? So this row pointer is just the natural way to do things. The first 3 elements is first row, right? So you can do whatever you are doing in the first row. Remember, like matrix multiplication, right? Matrix multiplication, first row times the vector gives you the first element, the inner product of these first row factor and the this factor give you the first element of the product. So this row pointer is very convenient, right? I know how much I can do, right? Immediately, okay? So just consider AX equal to B. You can see that row compressed storage is convenient if you implement this. You can probably know then why column is necessary. Okay, so if you do AB, B is a matrix as well, then A in the row compress, B in the column compress will be the most efficient, because that's how the operation is done. Okay. Okay. Yes. Go ahead.
So the value is the row number, right?
No, value is the actual double value. I should write 1.0. So value is double, right? This is 1.0. I use this number just so they don't repeat itself, so it's become clear. Okay. So this one is this value. This value is a double, and row pointer and column index are integers, right? For the location.
Then why is there a 6?
6 is your 1, 2, 3, 4, 5, 6. This one, right? The 1, 2, 3. 6 plus 1. This starts with the third row, right? This is a row index for first row, row index for second row, row index for the third row. Okay. This is row index for the fourth row, right? Okay. You're going to write a simple program and you can debug it very fast. Okay, this is something. Once you get used to it, okay, this also is a good exercise. When you change representations, your API won't change. Okay, so I'll show you that in your assignment, not today's lecture. Okay, so when you switch between two data structures because of more convenience in computation, okay, the API can stand as the same. Right? You can take a step back, okay? I'm a programmer, I'm going to design this package. All my interface will be defined by this more flexible storage, right? All the whatever APIs, assume you tell me the row index, column index, and the non-zero elements. But internally, I'm not storing that. Internally, I am doing something that's easier for computation. Okay, so I'll show you the example. Okay, yes? Column index is the same. It's the same as coordinate storage. The only thing changed from coordinate storage to row compress is the row index is changed to row pointers.
Like,
the column is the same.
So like this last row where we have 0, 1, 4.
Yes.
I mean in the first column there are
So value 4, value 1 is on the first column, right? So the column index is 0. Let's pick another one. 7 here, right? 7, the column index is 1. Right? It's just the same as the coordinate storage. Column index don't change. If you compare value and column index between coordinate storage and row compress, it's the same. The same. Okay. The only thing you deal with is the row pointers is assume a sorted row placement. So I store the increment when I jump rows instead of storing the row index. That's all, okay? But again, this is, the storage saving is minimal, but indeed in many computations, okay, many computations, it is much faster, right? Because when I deal with AX to B, I am using the first row only to times X, right? So the only thing I know is not loading in the row index, which is in this operation is the same. I don't load in that row index anymore in AX equal to B, right? The operation you're doing is this, right? So this gives you the first inner product for this, right? So here, when the most of my operation is AX equal to B, and a lot of your matrix things and problem solving, you just time a lot of matrix to a factor to see how it evolve. Okay, so in that case, okay, if AX equal to B is the most operations, A actually is most efficient to be stored in compressed row. Not because of the space savings, but you don't have to load in the row index. You are dealing with the first row anyway, right? Why every time you deal with it, you have to load the row index? Right? So this is more efficient in the way of computation. Okay. Yes, Minda.
So we have 6 rows and
5.
oh yeah, 5
Okay,
rows.
okay.
Why do we also need to have the very last pointer pointing to the position 12?
The 12 tells you how many non-zero element you have. The first 0 is not needed. I can agree. Okay.
Okay, so
12 is unknown though. I mean, for this matrix, it's 12. But it doesn't have to be 12, right? For a general 5 by 5 matrix, the last number doesn't have 12. Just tell you how many in total the number of non-zero elements.
yes, my question is just we have 5 rows, why we have 6 elements there? So it's
Okay, so okay. The first 0 it doesn't really need to be stored because always start from 0.
Okay.
Fine. So,
Okay.
but I just for clarity, okay, that's I use this, okay. But this 0 is not needed. This 0 is needed though, okay,
Yeah.
because the first row, the first column, maybe has an element, right? It can be 0, so I don't store it. So this 0 is necessary, but this 0 is not needed. True. Okay.
Why is 4 under 10 there?
Which one?
For the column index. Why? I thought 10 should be 3.
10? 10 here?
Yeah.
Do I do it wrong? Do I do it wrong? 10, 0, 1, 3. Yeah, I'm wrong. Sorry. 3. Yeah, sorry. The typo. Thank you. Thank you for your great eye. Typo. Nothing else. Nothing more than else. Okay. So maybe I should correct it. Typo. Haha. So you can see that typo happens. Right? This one, right? 9.
No, the other 10.
10. 10 should be 3, okay? Good, okay? Typo can happen in my PowerPoint. Typo can happen in your code as well, okay? It's part of the debugging process, right? Indeed, okay? So assuming that your program doesn't do what you imagine to do, it can be caused by typo, okay? Totally possible. Okay, you have a perfect algorithm, you have a perfect discipline, you have whatever, but you have a typo, and the program is still wrong. Okay, and you need to wait to check it. Okay, and this is a good example. You know, if you ask me to look at this for 20 times, I won't find it. Ito-han will find it in the second time she sees it. The same as the importance of program review, okay? Just like your writing, okay? Having your program to be looked by another person is usually a very good idea. Okay, it makes the program more robust. Okay? So don't write the program for yourself, okay? As last night, okay? Write the program from the very beginning. Assume that this code is going to be reviewed and presented to others. This is not my code. I'm writing a public code that people will check and use, okay? The mentality has to switch, okay? As a programmer, okay? Good. Okay, what's that? So these are, I already went through all this, okay? Saying that this is the good thing and bad thing about the coordinate storage and the compressed storage, okay? So let me just say that, okay, saying that one more thing in the sparse matrix is called symbolic structure, okay? Many times, coordinate storage is better for add and delete. Compressed storage is most of the time better for computation. It's faster, okay, because it's assumed a sorted structure, okay? It's a faster thing. But most of the problems, okay, back to our circuit simulations, the symbolic, meaning the location of the non-zero element, is actually fixed. Once the circuit is given, the way the circuit is connected is called the netlist. Okay? Once the netlist is known, before I know anything about the dynamics of how the circuit will perform, once you give me the circuit topology, okay, the netlist, okay, how the transistors connect to each other, okay. Once I know that, I know exactly where is the non-zero elements. Non-zero elements simply means that this element is coupled to the other elements, right? So it's symbolic. And for most practical problems, that symbolic matrix or the location of the non-zero element is fixed. Once you know the topology. I given a circuit before I give any transient pulse to predict its behavior. Once you give me the circuits, I set up my sparse matrix structure already. Anything later is changing the number in those non-zero elements. 0 will remain 0. Right? For sure, matrix operations give you new matrix that may not be sparse, okay? But the initial matrix, you can deal with it in symbolic forms. Because later on, updates is only updating on the value. This is actually much more permanent in most of the problems. Once the circuit is given, the matrix, the sparse matrix symbolic storage, meaning these two, is fixed. Finite element, once the geometry is given, everything is, all the symbolic entry is fixed. The value for sure will evolve, okay? But the form, the sparse matrix storage will not change anymore. Okay, so even for this, knowing that there is a symbolic things, okay, symbolic non-zero elements, many times we can use this to determine, right? Once I have the symbolic matrix, before I do some computations, like in circuit simulation, I probably run through 10,000 time steps, predicting how the transient happen, whether this voltage overshoot and that thing undershoot I want to study, how much power is this, okay? So a matrix will be used for 10,000 times. But that matrix symbolically don't change at all, right? So before I'm going to do that 10,000 steps of AX equal to B, I'm going to look at the symbolic storage of A and see how to optimize my operation. Remember, these are for large problems. Anything you can do on the symbolic level is going to cause great saving down the road. Right? This is operation is something, you know, if you handle the symbolic things well, you determine how this can be vectorized or parallelized well, okay, it can be a lot faster. Okay, so again, the symbolic ones, it's when you take your parallel programming, you are going to spend a lot of time in the symbolic matrix, okay? Because that tells you how the topological interdependence is, and you can parallelize or vectorize your computation according to the symbolic, and that is one time. All the next 10,000 computation, you know the data dependency in the symbolic non-zero entry. Okay? You will encounter a real example, okay? So common functions, okay, create just initialization with a known rank, add elements, delete elements, okay, retrieve an element, okay, return the rank of the matrix or where the count of the non-zero elements, okay, these are the common interface, okay, of a sparse matrix, okay. So I don't know if I have enough time. Okay, let's see how much you can raise. Okay, let's. I have a typo here. Sorry, this should be 3. Okay. Get these 3 vectors and implement me the retrieve. Okay. Function. To make sure you understand. Okay.
So given those,
you are inputting this factors. Okay, so this is supposed to tell you the full matrix, and then go through, right, retrieve 0, 0, 0, 1, 0 and things, print out my 5 by 5 matrix, including the zeros. Okay. just getting these three factors, okay, and program your print out your 5 by 5 matrix, okay. Should be doable. If you're very fast, it's about a 10 minutes assignment, 5-10 minutes assignment, okay. So try it, okay. Hopefully they won't bring back your horrifying memory of MATLAB calculating the different index. But this is like that, okay? It's a MATLAB index translation. This is 3, okay, let me modify it.
The retrieve element should give back the element at that.
Imagining you want to print out all elements in that format, right? So walk through all the possible row and index, right? Use this data structure to retrieve the value.
Every value.
Every value, including the zeros. When they retrieve NMN, right? When that is falling on, say, a 0 location, should print out 0. The retrieve function, right?
So the retrieve element takes no arguments
No, take the row index and column index, right? Of the matrix, right? You know the rank is 5. Okay. Yes.
Yeah. So based on the rank, so the row pointer there, that gives you like the rank of the matrix, right?
Yes.
The number of
That's
elements in there,
that's
not
rank
counting zero.
rank plus n plus
Okay.
1, right? Indeed. If you store the initial 0.
So we know the size of the matrix.
Yes. So as you just mentioned, right? If you actually in this format, if the size is the row pointer is rank plus 1. Has to, right?
Depending on if you store that first 0.
Right. So the rank of the matrix actually, if it's not degenerate, it's just in the information is in the size of your row pointers. The number of elements for sure is going to be also in the row pointer, right? The last element stores how many total non-zero element you have. The row pointers tell you the rank and the number of non-zero elements directly, just in this factor, row pointer factor. You're done?
No.
Okay. Okay, sorry for my own ill management of time. Okay, so if you understand the problem setup, please do finish. Okay, this will be part of your programming assignment too. Okay, so it's no time wasted. Okay, you're going to play with this a lot. So this practice is going to. My intention is to bring back your horrible memory. When you take your first programming class, you hate how this matrix index sometimes wrong. You're spending so many time in tracing how the index can be correct. I want to bring back that memory. Okay, maybe you have taken that class way too long ago, you forgot about that, okay? But if you implement the first time, most of the people, programmer, the index is somehow not correct the first time, all the different kind of errors. Okay, that's the horrifying memory I hope to bring back. Knowing that can be wrong, okay, important thing is how later on, when this matrix is 10 to the 7 by 10 to the 7, how do you verify the index can be correct? Okay, knowing that index can be so easily wrong, and if you just rely on your careful checking, that's usually not enough. Okay, so the next message that's going to come is that, okay, knowing that index can be easily wrong, how do you verify it? Okay, so please finish this assignment, and we'll continue on for next lecture.